Okay, so what I'm talking about is modeling of minerals processes. For today, -1 millimeters, so we're talking about spirals, magnets, anything that treats basically a muddy stream. And people have looked at this from various ways over many, many years. So I'll start off, what are some of the typical approaches that people have used to model fines processes? Then I'm going to introduce a thing called particle-based modeling, which is the way I've been looking at it, and show you why it's useful. Then we come to point number 4, conflict. Suddenly, once you start going down the line of particle-based modeling, you hit all sorts of conflicts, and how do you resolve those? Okay, so two questions. What modeling approach is sensible? What modeling approach should you use? And for today, why do I choose spirals? Well, the first one is you get things like fundamental modeling. This is when you look at discrete element analysis, or things like computational fluid dynamics, force balances. Here's a particle, F equals mg, what's the drag force? And you got out to really very, very detailed fundamentals. People have tried those type of models a lot. Statistical models, your partition curves. What's the chance that this particle will make it to product? There's that whole approach, probability approach. Then you get our favorite in minerals processing, the empirical, the heuristic. Measure it, run it, and measure it. You don't try and explain it too much. You just say, that's what happened. There it is. And there's a lot of models that are based on just straight measurement. So what should we be doing in today's age? Should we use any of those or combinations of them? And that's what I'm going to try and answer. As to the second question, why spirals? If you look at the quote here, spirals, they're very easy to run, but they're incredibly difficult to model. You got laminar flow, turbulent flow, you've got all kinds of things, forwards classification, reverse classification, thin film separation, all in one machine. So it's a good candidate to test a new approach on. So empirical, there's your typical spiral curve. It's mass pull versus your recovery for each different type of mineral. The problem is that for every spiral, you've got to repeat the test. For every head grade, you've got to repeat the test. If the locking of the feed changed, you've got to repeat the test. If the size, you've got to repeat the test. Luckily, the test is quick. So you can do these tests, and you can have charts for every spiral. How will it perform, for instance? But if you want to relate this data to a mill, and you ground finer, which chart are you going to use? So it's an approach limited to itself. Fundamental, computational fluid dynamics. Beautiful for Multotec hydrocyclone. Where's the flow patterns, the high pressure zones, the low pressure zones, the wear zones? On a spiral, not so much. There the guys managed to model where the water goes. But where do the particles go? Not so easy. Even if you couple it with DEM, how predictive are you? Maybe you can explain some things, but can you make a guarantee that's how it's going to work? Not easy, very complicated. Positron emission particle tracking. So what do you do here? You run your spiral, and you put a radioactive particle in the feed. And you can track where it goes down the spiral. So you can put a heavy particle in, or a light particle in, and you can see what happened very, very nicely, pick up subtle effects, but you're not going to have any predictive power. And here's the most common one, is your probabilistic method. For dense medium cyclones, for reflux classifiers, you've got your partition curves. And you can do every partition curve for every size class. They're quite useful. They're quite laborious to construct. You need to know the densities of all the particles and the sizes of all the particles. A lot of measurement. But now we're starting to be able to predict what's going to happen. Well, that's all very well for one spiral. How about a whole plant full of them and some recycles built in? So for many years, you would use what's called interpolation. So every one of those little dotted lines there is a spiral performance curve. And you might have a feed that lands somewhere in the middle. You can interpolate how well you think it's going to work. The approach falls down very badly, though, when you put a recycle stream in. You can see the pink line doesn't follow the patterns. It crosses over the other lines. And so when you start recycling, you might get the same head grade as the feed from a scavenger conch, but it's not going to behave the same. It might have different lockings, it might have different size distributions. So again, you come to an end there. So now we're going to get philosophical. We're going to say, well, what approach should I use? And this graph sort of shows effort versus reward or understanding. And so for many of these approaches, there's a little bit of effort you can put in. I'll do a size distribution. I can do that easily. I can assay the feed. I can do that easily. So for some information, you can get very quickly. But if you want to know what's the viscosity on the third turn of the spiral 3 centimeters in, how are you ever going to measure that? What we propose is then measure those things that are easy to measure, that are fundamental, sizes, assays, locking. Those that you can't measure the effect at the end. What I mean by that is, let me talk about a thing called emergent behavior. And I'll go a little bit into what that is. But it's a philosophy. It says, if I study an individual thing as well as I can, doesn't matter how well I know it, I can't explain a group of them. Okay. So an emergent property is a property which a collection or a complex system has, but the individual members don't have it. Okay. So let's say I've measured my particle size, my particle density. If I put them all together, what's going to happen? And the emergent theory says you might as well go measure the overall effect. You're not going to predict it. So let's give some examples. In maths, if you know what is the formula for the circumference of a circle, 2 pi r, I can integrate that to get the area of a circle, pi r squared plus the constant. The constant's naught. There's no emergent theory here. If you know that, and you know everything. If you're looking at movement of gases, nitrogen, oxygen, you know how fast the particle is moving, an individual particle. You know how many you've got? You can predict what's happening in the balloon, millions of them. There's a pressure, depending how fast the particles are moving, the balloon expands, it contracts. So there's a little bit of unknown, but if you understand the molecules, you understand the balloon. Now you mix hydrogen and oxygen together. Oops, you get water. Could you have understood that you would get water by understanding 2 gases? There the emergent behavior is very big. If I study the behavior of one person and I put them in a crowd, suddenly their behavior starts to change. And this is again all the concept of emergent behavior. How hard do I have to study one person to predict what he'll do in a crowd? The effort is huge. Rather just measure what he does in a crowd. Okay, so there's 2 worlds. So we now want to talk about particle-based modeling. We're going to have 2 things we're going to look at. We're going to use the concept of emergent behavior. First of all, we're going to use the microscope or the MLA microprobe, and we're going to measure thousands and thousands of particles at the separator feed and product. So there we're gathering fundamental data. Every particle, what's your size, what's your density, what's your shape, who you lock to, etc. And we'll also measure the overall performance of the separator. And the model that we use must join those 2 worlds. So we use a thing called particle tracking analysis to gather the particle data. What that is that when you take a sample to the mineralogy department and you say, please tell me what's in here, they make a little section like you see there. Often they're little circles. We make bigger ones, little slabs. And there's maybe 100,000 particles on that slab. And we say to them, please give me the information of every particle. Don't summarize it. I want everything back, please. And I want that for the feed, and I want it for the spiral product, and I want it for the spiral tail. Now I can track what green particle looking like a triangle, where did it go? So I've got a lot of information to track the performance of that spiral on a fundamental basis. So there you have it. You've got to check this against reality. Remember, you're only making a little section. You're looking at 100,000 particles. Maybe it weighs 2 grams. How well does my 2 grams represent reality? So you've got to be careful. Let's do a size analysis with sieves. Does my size analysis agree with my autoSEM analysis, my microscopic analysis? Do the head grades tie up? So there's quite a lot of reality checks you have to do to verify that what you're measuring under the computer makes sense. What's nice is though you can do error analysis. You can add more particles and say, well, did I get any better, or I didn't learn anything new? So you've got a very good statistical handle on how well you're doing by looking at particles. I just mentioned many issues. What happens if the particles are porous? What density did you give them? How will I represent triangles versus logs versus squares? Usually they make everything into a nice little circle and give you the circle diameter. But I want to look at shapes. The spodumene petalite separation may be an example that you guys are doing. Okay? And how do I handle this data? Do I handle it in Excel? Do I handle it offline? How do I manage 100,000 particles? So here's some examples. On the one graph, you got a feed size distribution using sieves. On the other one, you have a feed size distribution by the MLA, by the computer. And with a bit of practice, you can start getting it right. Okay? Maybe you've got to do more size classes. You've got to do stereological corrections. But you can get pretty close. Now, once you've got all the data, you can mathematically sort it. You have 100,000 particles. You can sort the cleanest to the dirtiest, the densest to the lightest, the coarsest to the finest. And you can write down what's possible. Not to say the spiral will get that, but what's available for me. If I had a perfect plant, what can I get? And those are the target graphs that you can draw. You get excellent liberation data. The most powerful thing you get from the MLA is who is locked to who. Is this piece of chromite clean? Is it attached to a peroxenite, a piece of clay? You get all the associations in detail. Have I milled it correctly to even bother with my spiral? That sort of data. You can zoom into any mineral, any shape, any size, and see what you've got. So it becomes very, very powerful. The problem now is how powerful is the model that can handle all that data? That also has to improve. Colors is lovely. You can say, I want all my valuable mineral to be pink, please. Let's just track them visually. What happened? Where did the pink particles go? Are they rounded? Are they square? So you get quite a nice feel for how you're doing as well. Shapes. University of Cape Town has done lovely work on how do you have constant shape factors. Many shape factors apply for a size fraction. So a triangle might have a shape factor of 0.5, only if you're a millimeter. If you're half a millimeter, a triangle is 0.2. Doesn't make sense. How do you have shape factors that you can use that make a triangle the same number at any size? And these are the kind of things you can look at: aspect ratio versus roundness. And you can start seeing what shapes went where. When this process began, we said, sorry, Excel, you can't handle 100,000 particles. It's too complex, too slow. Let's summarize everything into size classes, into density classes, into liberation classes. And that all works well for a simple separator. But now you want to do flotation. Now you need surface properties. But if you summarize it by size or you summarize by density, where's your surface property? You've lost them. So we abandoned the approach of grouping things into size classes and density classes to keep every particle's information untouched. And the only time you ever summarize is at the very end when you want to look at the overall graph. What did I do? So your summaries are your outputs are in summarized form, but you leave all the particles alone. So if you send it from a spiral to a magnet, you've kept every particle's magnetic properties unsummarized and you can use them. Here, for instance, is some of the partition curves we're getting for various mass pools across the spiral. So for a very small mass pool, more, further, till you're pulling everything to concentrate. And you can see a spiral performs very nicely across a narrow band where all the curves lift up nicely. A different spiral may have different shapes. A spiral under a viscous medium and a spiral under nice clean water also may have different shapes. The particle data never changed, but the emergent behavior certainly did. And so how can you tie those two again through your model? I think I've said some of this already. What we do though is we link Excel to Python. We keep the data, all the particles offline, because it's very slow, and you say to Excel, a little routine, Python, go and call those particles, bring back for me the triangular ones, put them back into Excel. It makes things very much faster, and the learning process is very quick because you're not learning a new package. It's still all interfaced through Excel. We've got quite far. Spirals, reflux classifiers, hydrocyclone screens, flotation, very, very interesting because you've got surface properties and bulk properties. So what does liberation start to mean? It changes its name. So we've gone quite far down the line with various types of separators. So that's all very well for -1 millimeters, but now what about a mil? What about going coarser? Can I use this approach to look at rocks? I can't put rocks under a microscope, but can I still classify them in the same way? Can I classify them by size, by shape, by what they lock to? And you find that you can. You can also go tiny. You can say, let's look at PGMs, 5 grams per ton. Very, very, very low amounts of mineral to look at. And they're tiny, they're 2-3 microns big. Can I stitch them onto the minerals that they're locked to? Can I group these minerals and make rocks? So once you start from particles, you can go smaller and you can go bigger. You can link different worlds through particles and through minerals rather than through assays. Okay. Very useful in the geometrological approach where you're looking at variability. It's very quick to say, I will now build a new particle data set with a higher head grade or a different composition. How does the model apply to that? So on the left-hand side, you have some PGM data from a typical PGM search. Yes, you can tie it in. On the right-hand side, hyperspectral images, so it's giving you the locking data of nice big pieces of core, and you can relate that also back to your minerals. So you can go much coarser and look at crushers and mills using the same approach. And then everything fell down, because now you have conflicting data. You have a size distribution giving you a sieve analysis, but I got a size distribution from the computer. I've got a chemical assays that I measured in the lab, but I got a reconstituted mineralogical chemical assay. They don't agree. I've got XRD data, I've got microprobe data, I've got all kinds of data. How do I reconcile this that I can believe it with one set of data, not changing all the time? And what it means that you start having to build your own particle lists. Stats comes in, texture comes in, looking at 2D sections doesn't give you the correct information for liberation. It gives you a partial view because you've cut through the stone. You haven't got the complete liberation aspects of that stone. Things like roughnesses. So there are shortcomings that you've got to watch out for, that you've got to correct for. Here's an example. The data on both left-hand sides are data directly measured looking at the platinum group minerals that are at different size classes. But they're all wobbly graphs and chunky sort of lines. Does it really exist in nature in a chunky form like that? No, it's because there's such a few data that if you measured more and more and more, it would smooth out. Well, let's use smooth data then and fill up the holes. Okay, so I'm getting a bit philosophical again, but you can fix the data, not fix it, but build it better than a partial view gives you. Once you start doing that, you have a very powerful weapon in your hand. You can correct for missing data that you didn't get. All of this then puts together, and it builds you a coherent data set where every mineral has its own inherent size distribution, how it's locked, how it occurs. On this graph, you can see the talc, the blue line, is finer than the other minerals because it's softer. So yes, you confirm this mill broke the talc finer, the orthoperoxine's the hardest, it stayed coarser. If I milled it differently, what would happen? You get a very, very high degree of resolution on your data. Okay, so that was quite heavy. But what I really wanted to get to was many approaches are available. This approach has two legs, fundamental and emergent behavior, but bring data in from all over the place. Don't just believe what the microscope tells you. Okay. And many pitfalls, still a learning process. But we are now putting flow sheets together, go and audit a real plant, compare that data to what a batch piece of data did, what happened, what emergent data showed up. The batch is the same, the particles are the same, so the changes have happened because of emergent effects. Now, what about the future? Microtomography, where you take 3D data directly into the model. You don't have to try and build particles, you can get them straight away from X-ray tomography. It can't do it yet, it's still on the journey. It hasn't got enough resolution, but maybe that space will be able to bring 3D data straight into the models rather than only 2D data. That was it. Thank you. I hope you had a flavor of what we're doing.